Okay, let's talk about inverse functions for a little while. A couple of key pieces here. Inverse function is a one-to-one function. That's going to be a surprisingly big deal. We'll talk more about that in a second. In which each output corresponds to one input because it's a function, and every output to one input, every input to one output. That's one-to-one. Horizontal line test tests that. So, for example, if you look at x to the third, x to the third passes the vertical line test, so we know it's a function, but it also passes a horizontal line test. Any horizontal line only passes it once, so it's a fully invertible function. It's one-to-one over its entire domain. As a counterexample, if you imagine x squared, good old y equals x squared passes the vertical line test, but horizontal lines pass through multiple times. So technically, x squared is not an invertible function over its entire domain. You might think, well, what about the square root? Square root undoes x squared, right? And you would be right. But if you remember what the graph of the square root of x looks like, the graph of the square root of x looks like that. Well, that is the same pieces as we have here, just switched so the inputs become the outputs and the outputs become the inputs. Great. But what happened to this other part? Well, if we wanted to turn all of x squared into an inverse function, we'd have to flip it down there as well, and it wouldn't be a function anymore. This is why square roots aren't allowed to deal with negative numbers and still stay real, because we only allow, when talking about x squared and the square root of x as inverses, we're only allowed to do that when x is greater than or equal to 0. If x is less than 0, in the reals, it doesn't have a square root. It's not invertible over this huge part of its domain. That's going to become super important very, very shortly. But the big thing about what inverse functions do from a conceptual point of view is that they undo each other. They reverse the other, like x squared and x. Sorry, like x squared and the square root of x. They reverse each other's operations. And you've seen, some of this, how to reflect, and you look at what the graph should look like. And you have some experience probably in your Math 111, your Math 95, about ways to go about building them. So, for example, if we wanted to build an inverse function for y equals x to the third minus 2, really all it is solving for that input variable and making that input variable your output variable instead. So you often see people, just to stick with convention, they'll change their x's and y's to change their inputs to outputs and then solve for y. So they'll get x plus 2 equals y to the third, so y equals the cube root of x plus 2. But it's important to remember that this x is not the same as these x's. This y, as soon as we flip them, we're changing what we mean to be x and y. So, for example, if this x was time, say in seconds, and that y was dollars, then by the time we're down here, well, this function took in time and put out dollars. Its inverse had better be taking in dollars and putting out time. We switch the x and y so we can graph them on the same axes, But it's kind of a dangerous thing to always do because it hides the fact that the meaning of that domain and range are what's switching, not just the symbology. So I'll reinforce that as we go along, but do be careful about that. These x's and y's aren't the same thing. And if you think about it in terms of the graph up here, heck, even when I graphed the x squared and the square root of x squared, of course, does have both pieces. If the square is the area and the square root is a length, then, is this the length and that's the area, or is that the area and that's the length? Well, for this graph, the input is the length and the output is the area, but for its inverse, the input would be the area and the output would be the length. So I always thought graphing them like this on the same axes was a little bit disingenuous, because it kind of ignores the fact that the meaning of our inputs and outputs have changed. It's a good tool for trying to learn how to solve, to build functions, and how to get an idea of what an inverse function should look like. But frankly, it's a little dangerous when it comes to the meaning of our functions. And we'll talk more about that as we go along. The big key is that all of our trig functions essentially have all had the same job. All of our trig functions, I'm going to use the word trig here just for all of them, but so this could be sine, cosine, tangent, secant, cosecant, cotangent, any of them. All of them have been taking in an angle and outputting some ratio. Either a ratio of side lengths in a triangle, a ratio of coordinates on the xy plane, whatever that ratio happens to be, our trig functions have been taking in that angle and giving out the appropriate ratio depending on which function we use. Thus, our inverse functions, the trig inverse functions, have to undo that. So they have to do the opposite thing. They have to take in a ratio and give back some angle depending on which trig function we're looking at. So as you look at your inverse functions, I want you to keep that in mind. If we were dealing with an inverse function, its input has to be a ratio and its output has to be an angle. If we're looking at our sine, tangent, cosine, or straight trig functions, then the input has to be an angle and the output's a ratio. Now, so that's kind of what we're looking at up here in terms of the meaning of y equals the sine inverse of x, is that x equals the sine of y. So for example, if I say the sine inverse of pi over, well, I can't ask the sine inverse of pi over 6 because it's got to be a ratio. The sine inverse of 1/2, if I say that's equal to pi over 6, well, that means, according to this definition, notice that we change from the sine inverse to the sine. That means that the sine of pi over 6 had better equal 1/2, and indeed it does. So that's really all that the sine inverse is asking. It's asking, what angle does sine use to output a 1/2? Essentially, the sine of what is 1/2? Well, the sine of pi over 6 is 1/2. If I asked the sine of what is, I don't know, square root of 3 over 2. Sine inverse says, well, given this ratio, what does sine need as an input to give that ratio? Well, it needs pi over 3 to give that ratio. Because the sine of pi over 3 is the square root of 3 over 2. So this is true because that is true. Now you might have already thought of, or occurred to you, what one of the big problems might be. Pi over 6 is not the only angle for which sine gives you 1/2. If we look at a graph of sine, I'm going to pull this away for a minute. If we look at a graph of sine, we all know what sine looks like nowadays. And if we look at 1/2, sine equals 1/2, sure, at pi over 6, but also at 5 pi over 6. And over here at, what would that be, 13 pi over 6. And 17 pi over 6. It equals 1/2. Also, over here at negative 7 pi over 6. There's really infinitely many places, infinitely many angles, for which the sine of that angle is pi over 6. And that's a problem. If I'm asking, or the sine of that angle is 1/2. If I'm asking the sine inverse of 1/2, and this is supposed to be a function, functions are only allowed to have one answer, and only one answer. So just like for that square root of x, we need to restrict the domain of the sine function to a place that it passes a horizontal line test, so we can say, okay, the sine inverse only exists in this range of angles, so that each sine question, each sine inverse question, has one and only one answer. And we could have done that in multiple different places if we wanted to, but the most useful and helpful place to do that is there. Is between pi over 2 and negative pi over 2. This is essentially in quadrant 1 and the negative version of quadrant 4. As far as the inverse function is considered, none of the rest of sine exists. The inverse function only knows about angles within this small range. So even though we might be thinking, hey, I want an angle for which sine gives me 1/2, well, sine of 5 pi over 6 is equal to 1/2. Can't that be an answer? It can't. The sine inverse doesn't know about anything outside of this range. Sorry, that's negative pi over 2. It has to give an answer within this range. Luckily, everything from 1 to negative 1, all possible sine outputs are in that range. But we have to give the one answer that exists within that range. Similarly, if we were asked for the sine inverse of something like, well, negative square root of 2 over 2, you might look at your unit circle and see, hey, down here at 5 pi over 4, we have a y value of negative square root of 2 over 2. I don't know why I wrote that so small. So how about 5 pi over 4 for an answer? Well, 5 pi over 4 isn't in this range. 5 pi over 4 is way over here. So I said quadrant 1 and quadrant 4. So what about here at, say, 7 pi over 4? Well, at 7 pi over 4, it also has a y value of negative square root of 2 over 2. So is 7 pi over 4 an okay answer? Well, no. 7 pi over 4 is even further out. 7 pi over 4 is over here somewhere. It's got to be between negative pi over 2 and pi over 2. So it can be in quadrant 4. Technically, it can be in quadrant 1 or in quadrant 4. but because it's negative, we know it has to be in quadrant 4. It has to be this little negative pi over 4 angle over here at negative pi over 4 to get that negative square root of 2 over 2 value to pop out. So we have to be very careful about this. Now, surprisingly enough, we are kind of used to that. If I ask you what's the square root of 9, you're not going to tell me the square root of 9 is negative 3, because we know that can't happen. When we do square roots, we only get that one answer, that positive 3. We've agreed to always give out the answer on the positive side because that's our restriction for the inverse square root. Do be careful. It's not plus or minus 3 either. It's a function, so it's only one answer. We have to do the same thing with the trig functions. It's just the restriction is more dramatic. That restriction is just enough to be able to get all of the answers occurring once and only once. So that's why we're restricted to that range of negative pi over 2 to pi over 2. We essentially have to cut this off here and here so we don't get multiple answers occurring, which is why our inverse function is just, that little part between negative pi over 2 and pi over 2. Its inverse image still passes the vertical line test. If we'd have allowed this to go back down, then this would have to curve back down and we wouldn't pass the vertical line test anymore. So it's a very technical restriction, but it is an important one. As I said, we have to do that for all of the trig functions. We have to do it for cosine as well. But because cosine has a different shape, it needs a different restriction. We know that cosine normally looks like that. Well, not quite like that. Normally looks like that. And again, is not a one-to-one function. Doesn't pass a horizontal line test. So we need to restrict it such that we get all of the answers, but we get all of the answers only once. If we kept the restriction from negative pi over 2 to pi over 2, it wouldn't work because we would get all of these answers occurring twice, which would make it not a function, and we would get none of the negative outputs. So instead, we restrict it from 0 to pi. That way we get all of our answers, sure, but we get all of our answers only once. So, similarly, if somebody asked for the cosine inverse of negative 1/2, well, again, we'd look at our circle. We know cosine ratios are negative in quadrants 2 and 3. So there's certainly a quadrant 3 angle down here that has a 1/2 and a square root of 3 over 2. And if you looked at what that angle is, it's, 4 pi over 3. So it's true that the cosine of 4 pi over 3 is negative 1/2. But 4 pi over 3 is not within this restriction from 0 to pi. We've got to be in the first rotation, quadrant 1 and quadrant 2, for our angles for cosine. So while it's true that the cosine of 4 pi over 3 is negative 1/2, the inverse function doesn't know that angle exists. The inverse function only understands, or only can output, angles between 0 and pi. So we have to find an angle within that restriction that also has a negative 1/2. It happens to have a positive square root of 3 over 2. This was negative. and that angle is 2 pi over 3. So that 2 pi over 3 is the only answer that the cosine inverse of negative 1/2 can give. Similarly, we're going to have to do the same thing. The nice thing is secant uses the same restriction for cosine, naturally, because they're reciprocals, and cosecant uses the same restrictions for as sine because they're reciprocals. Tangent in some ways is a little bit nicer. I'm not sure if nicer is the right word, but a little bit cleaner in some ways, because if we graph tangent normally, you remember tangent had kind of all of these sweeps in it. But again, it doesn't pass the horizontal line test. It wouldn't be invertible over its entire domain. But it's in some ways much more natural to just, well, let's restrict it to one of those sweeps. One of those sweeps goes through its entire range of values from negative infinity to infinity. It's a funny looking infinity, sorry. So if we just kind of restrict it to that one big sweep, we can get all the possibilities. So that's not so bad. And in some ways even nicer. Remember, those asymptotes are at pi over 2 and negative pi over 2. So its restrictions are the same as the restrictions that we would have for sine. So that's nice, I suppose. But again, remember that that's quadrant 1 and essentially the negative version of quadrant 4. So on your unit circle, if you're looking for angles for tan inverse, it's got to be in either 1 or the negative version of quadrant 4. It being in quadrant 4, you can't use just something coterminal. It's got to be all the way down there. For example, if somebody asked, what's the tan inverse of negative 1? Well, while it's true that down here, where we've got negative root 2 over 2, negative root 2 over 2, well, that would be positive 1. So, while it would be true up here, negative root 2 over 2, positive root 2 over 2, at 3 pi over 4, the tangent of 3 pi over 4 is indeed negative 1, but the tan inverse doesn't know about that angle. The tan inverse only knows about angles in this range between negative pi over 2 and pi over 2. In quadrant 1 and in the negative version of quadrant 4. So we have to be down here in quadrant 4. But again, we can't use the 7 pi over 4. 7 pi over 4 it's pi over 2 pi. 2 pi's about here. So 7 pi over 4 is way out here. It's way outside of this restriction. But over here at negative pi over 4, we will get a negative 1. So the inverse function, and if you zoom in on this and you go to a negative 1, I can't even see that. Where's negative 1 and 3 pi over 4? That's why I don't like graphing on the same axes. They got to be flipped. But either way, we have to use that one that's within that range, so we have to have this yield the negative pi over 4. So that is something we'll have to be careful about, and takes a bit of getting used to. It is nice that sine and cosine, it is nice that sine and tangent are the same from negative pi over 2 to pi over 2, though the tangent one, you'll notice, the tangent one, notice this doesn't have equals on those, just has less than and less than, or this has less than or equal to, less than or equal to. That's why that has square brackets, and why this should have parentheses. Because the asymptotes at negative pi over 2 and pi over 2 mean tangent's not defined there, so to be super technical, that restriction should be shouldn't include those endpoints. It's not a huge oversight, but it's a little one. So you'll see me try to keep those restrictions in mind as we go along. And as I said before, for secant, cosine, and cotangent, we'll just use the same restrictions as we did for their reciprocals. So, for cosecant and secant anyway. Secant's cosine, so from 0 to pi. Cosecant goes from negative pi over 2 to pi over 2. It is true that cotangent shifts over to 0 to pi again, but I don't think I've ever used cotangent inverse in 30 years. But if you remember the graph of cotangent switched to its asymptotes looking like that. So it is natural for the restriction to change to being from 0 to pi. But yeah, we don't do a lot of cotangent inverse. So, if we want to find these exact values over here, do have your unit circle with you while you do these. So the sine inverse of the square root of 2 over 2, well, we grab our unit circle. We know sine is positive. Remember, these are the ratios for sine. So what angle makes sine output this ratio? Well, we know sine is positive up in quadrant 1 and quadrant 2, but the inverse is only defined in 1 and 4. So this problem has to be happening in quadrant 1. It's the only place the inverse is defined and sine gives something positive. So if we look at our unit circle to where the sine value, the y value, is the square root of 2 over 2, you'll see that happens at pi over 4. So that had better be pi over 4. Arc cosine, from your reading, the arc and the cosine inverse, they're just two different notations for the same thing. So this could be written as cosine inverse of negative square root of 3 over 2. There is a slight difference in the notation in higher end applications, but it's not especially relevant to us, so try not to worry about it. So the cosine inverse, cosine is negative. Well, we know cosine is negative over here in quadrants 2 and 3, but we know the inverse is only defined in 1 and 2, between 0 and pi, so this has to be happening over here in quadrant 2. So you look over in quadrant 2, and you look, where is the x value? Negative square root of 3 over 2, and you'll see that happens at 5 pi over 6. And 5 pi over 6 is between 0 and pi, so 5 pi over 6. Cool. Now, this is fun. I said we don't use the secant, cosecant, and cotangent that often. We certainly do. We certainly can. And there are a lot of applications for it. But remember, the secant and the cosine are super linked. So if the cosine of some angle is equal to a over b, then the secant of that same angle has to be equal to b over a. We know they're reciprocals of it. But remember, this inverse function is acting on these ratios. That means the secant inverse of negative 2 is the same as the cosine inverse of negative 1/2. It's reciprocal. And that's crazy. That we can just do that. And if it helps, remember, if y equals the secant inverse of negative 2, that means the secant of y has to equal negative 2 by definition. That means the cosine of y has to be negative 1/2 because of the reciprocal identities. And then if we redid the inverse, that means y equals the cosine inverse of that negative 1/2. So it's a perfectly legitimate thing to do, and allows us to really only worry about, in terms of inverses, sine, cosine, and tangent, unless we want to be playing with the other one, which is the big reason you especially never see cotangent. But again, cosine inverse, cosine of a negative ratio, that means it's got to be over in quadrant 2. Can't be in 3 because the inverse function doesn't know about 3. So we'll be looking for an angle with an x value of 1/2. And that's going to happen at 2 pi over 3. So 2 pi over 3. Number 4 here is even more fun because we can kind of do the same thing. This is cosecant, so we can change that into a sine inverse of this thing's reciprocal, so 3 over 1, or 3. And as soon as we say the sine inverse of 3, what angle makes sine output 3? It's not possible. It never happens. That's undefined. Remember, sine goes from 1 to negative 1, right? It's trapped in there. And even more than that, we're only considering this part of it. So if somebody asks, well, what angle makes sine output a 3? Well, it never does. Not without amplitude changes and stuff that aren't on here. And we'll deal with those when we deal with solving, so don't worry about that. So that's really common. Remember our domain and range from our other section. The sine can only output something from negative 1 to positive 1, so the sine inverse can only input something from negative 1 to positive 1. So that problem just has no defined answer, and you're done. And that's it. Now, down here, find our inverse function. This is a little bit like our solving, and we'll talk about our distinctions between this and solving a bit later, like in a couple days. But we're going to essentially approach it the same way we found inverses before. And the nice thing is, most of the kind of tools that you've been playing with for solving work. If we're trying to solve for this x, well, you subtract 1 from both sides. Y minus 1 equals 3 times the cosine of x. Divide both sides by that 3. Y minus 1 over 3 equals the cosine of x. And as soon as we have that cosine isolated, we can take the cosine inverse of both sides. We have to be careful. This has to be within that restriction from 0 to pi for this cosine inverse of cosine to give us x. But since we're told it's within that range, cosine inverse of cosine of x gives us x. They undo each other, leaving us with the cosine inverse of y minus 1 over 3. That's the inverse function. It's similar, I know I keep bringing this up, but it's similar to square roots. If somebody said, plus, if somebody said solve this for x, well, you'd subtract the 1 from both sides. Then you'd divide the 3, And as soon as you isolated the square root, you would perform its inverse and get x equals y minus 1 over 3 squared. But this is all only valid if x is greater than or equal to 0. If x was a negative number, then this square root wouldn't be a thing. So we wouldn't be able to, square root its square and just get itself, because the square root wouldn't be real. So it is more dramatic than it is with square roots, but it is a kind of thing that you've done before. And just like we used things like this when we solved and had to compensate for it, and again we'll talk more about that when we get into solving, to compensate for the domain restrictions, we'll have to do something similar when we start solving. But right now we're just building inverse functions. So we would finish this by switching our x and y's and getting cosine inverse of x minus 1 over 3, and then saying our inverse function, f inverse of x, is the cosine inverse of x minus 1 over 3. Sorry, I went on a little side quest there, but hopefully it was useful for you. And that does highlight one of our, starting to have some troubles, highlights some of our kind of meaning here for our functions, for our inverse functions. This idea that the cosine inverse of the cosine, that those undo each other giving x, that is part of the definition of what it means to be an inverse function. But we do want to keep in mind that it's only true when we're within our proper restrictions. When our ratios are between -1 and 1. Notice here x is a ratio because it's an input for an inverse function. And our angle is between -pi over 2 and pi over 2. Notice this x is an angle because it's going into the sine function. So these things will undo each other within the proper restrictions. If it's not within the proper restrictions, and we'll see that happen real quick, if it's not within that restriction, we'll talk about what we do. Tangent can output any ratio, so it doesn't have a ratio restriction, but still has an angle restriction. So, find the exact value of the expression. It would be tempting to say, hey, the sine inverse and the sine undo each other and just leave us with the -7 pi over 6, but that can't happen because -7 pi over 6 is not in sine's restriction. Now that doesn't mean we don't do anything. That means we have to find the angle within the restriction that gives us the same answer. For example, if we look at -7 pi over 6, -7 pi over 6 is right there. So -7 pi over 6 is coterminal to 5 pi over 6. So that means the y value is 1/2. So we'd have to look somewhere within our restriction, so somewhere over here in 1 and the negative version of 4, where we also have a y value of 1/2, and that would happen at pi over 6, because that also has a y value of positive 1/2. So the sine inverse of the sine of -7 pi over 6 is actually pi over 6. It's the value within the restriction. And if you want to see, that seems weird, it should seem weird. But if you look at, say, what is the square root of -5 squared, It might be tempting, again, to say if we, the square and the square root undo each other, so this is negative 5. But the square root doesn't know about negative 5. That's not possible. But it can output something else whose squared gives you the same thing that negative 5 does. Negative 5 squared is positive 25, and the square root of positive 25 is 5. It's not plus or minus 5. It's just 5. Again, it's not as dramatic of a change as from negative 7 pi over 6 to pi over 6, but it's the same idea. And that takes some being careful with. Again, in number 2 here, we might think cosecant of the cosecant inverse of 1/2 is just going to undo each other and give us 1/2, but it can't. This is the cosecant of the sine inverse of 2 from our discussion before. The reciprocal is the reciprocal ratio, so we just took the reciprocal of that ratio, and 2 is not within negative 1 to 1, so this isn't possible, so it's just undefined. We can't even move it to some place that is possible. If the ratio's not right, we can't do anything, and we're just done. These are some of my favorite problems. I love these. That's a hint. Whenever the teachers say they really like a type of problem, it means it's good to be good at those. Kind of brings everything together, too. So, cosine, the sine of the cosine inverse of 1/3. Well, we know the cosine inverse is only defined in quadrant 1 and quadrant 2, because it's only defined between 0 and pi. So we have to be somewhere in those two quadrants. We also are looking at a ratio for cosine that's positive. And we know cosine is only positive in quadrant 1 and quadrant 4. So the positiveness of the ratio tells us we have to be in one of these two quadrants. The cosine inverse tells us we have to be in one of these two quadrants. The only place they overlap is here in quadrant 1. So that means we have some angle over here in quadrant 1 such that the cosine is outputting a 1/3. Well, if the cosine's outputting a 1/3, sine and cosine can't automatically undo each other, but that doesn't mean we can't, learn or build some things. If the cosine is putting out a ratio of 1 to 3, that's an x over r, or an adjacent over hypotenuse if you want. So that's an x over r. Well, to find the sine of whatever this angle is, or something else coterminal to it, whatever that angle is, we know the cosine gave us 1/3. If we want to know what the sine value was, we would need this y value over here. Well, a little Pythagorean theorem will give us that. Plus b squared equals 3 squared, so b squared is 9 minus the 1, so b squared is equal to 8, so b is equal to plus or minus the square root of 8, which is plus or minus 2 square root of 2. Now, notice I'm still doing plus or minus here. How do we know whether it's a positive or a negative? Well, we know we're in quadrant 1, so we know that has to be positive. If we were down here in quadrant 4, we'd have to use the negative 2 square root of 2. So it is important to figure out what quadrant we're in. So be very careful about that. So what is the sine for an angle that builds this triangle? Well, it's y over r, so 2 square root of 2 over 3. 2 square root of 2 over 3. The key to doing these really is drawing that diagram in the right quadrant so we can make an argument. Notice we never figure out what angle this actually is, because remember, cosine inverse, so that's taking in a ratio and outputting an angle. So this is some angle, and we're being asked what the sine of that angle is. But we never find out what that angle is. The only thing we have to know about that angle is that it builds this triangle. Once we have that triangle, we can tell you what the sine is, or tangent, or anything else. It can even go a little further. Sine, I think this is our last one. Yeah, nice. The sine of the arctangent of x, and again, I'm going to rewrite this. Sine. I don't care which one you use. You can use either one. I'm going to tend to use the inverse notation just for consistency, but use whichever one you want. Now this one's a little more obscure. Tangent inverse we know is between negative pi over 2 and pi over 2, so that's got to be in quadrants 1 or 4. So between negative pi over 2 to pi over 2. But we really don't know whether it's in quadrant 1 or 4, because we don't know if that x is positive or negative. That x could be negative something. So I'm going to draw it in quadrant 1. But keep in mind the idea that it could be down here. We will just have to be careful. Now, tangent, the ratio of tangent is just the value x. Well, the tan inverse of x equaling some angle means the tangent of that angle has to be x. So that x is a y over x, or better yet, an opposite over adjacent, just because I don't want two different kinds of x's there. So if this is our angle, then that's x and that's 1. If the x value happened to be negative, then the x would be down here, and it would just be a negative number down there. But notice it would still be a positive 1, because we're positive in that quadrant. So we haven't lost generality yet. And if that's x, if that's 1 and that's x, a little Pythagorean theorem will give us this other side. So 1 squared plus x squared will equal our r squared. So r is technically the plus or minus 1 plus x squared, but because this is a radial value in r, the r's are always positive, so we can use the square root of 1 plus x squared, whether x was negative or positive. So it's still, if x was negative, then okay, our picture would be down here, but this would still be x, that would still be 1, and that would still be a positive square root. So it doesn't change anything for us. And we want to know the sine of this angle. Well, sine is supposed to be opposite over hypotenuse, so the opposite is that x, positive or negative, and the hypotenuse is that square root of 1 plus x squared, so that is the equivalent algebraic expression. Very similar to the problem above, but just a little more sophisticated because we have to do it in general. It's just all the same tools. Just here we didn't have a value for x, so that's a variable. You'll end up doing a lot of this for those of you going into calculus. This kind of thing happens quite a bit. Okay, these inverses take a lot of playing with, and dealing with these restrictions and remembering these restrictions takes a fair amount of playing with. The biggest thing I can tell you to focus on at first is understanding this idea of what are these inverse functions doing. The job of an inverse function for trig is to, the normal trig functions take in angles and gives out ratios. our inverse functions take in a ratio and give out an angle. So if you can keep that in mind, that should go a long way to helping. Okay, hope this helped. There are notes for the solving coming up, but doing these in multiple parts I thought would be good. So, have a beautiful day, and let us know if there's anything you need.